Welcome to the Explainer. Today, we're unraveling the invisible mechanics that make the entire internet work. You know, behind the scenes of literally every website you load, every multiplayer game you play, and every video call you make, there are two wildly different delivery couriers working tirelessly to move your data all around the globe. They're called TCP and UDP. And getting a handle on how they operate is the absolute key to understanding why our networks behave the way they do.
We've got a great roadmap for this explainer. First, the Internet's delivery services. Then, TCP, the reliable courier. Next, the TCP three-way handshake. After that, UDP, the speedy sprinter. And finally, real-world protocol trade-offs.
Okay, let's dive into this. Have you ever noticed how you can be on a live video call and suddenly the screen freezes, or half the frame turns into a pixelated mess? Yet when you send a 10-page email, it arrives on the other side absolutely perfect, not a single comma missing. Well, that discrepancy isn't a random accident. It's entirely by design, and it's based on the specific delivery protocol being used under the hood.
Section 1. The Internet's delivery services.
To really grasp why this happens, we have to set the stage by looking at the bustling shipping department of the Internet. It's called the transport layer. Every single time you click a link, stream a movie, or shoot a target in an online game, your data is being chopped up into these tiny little pieces called packets. These packets are sent straight through this critical layer. The transport layer's entire job is to figure out exactly how these packets should be sent and received, and it basically gives applications two very distinct choices for how to ship that data.
Section 2. TCP, the reliable courier. The first choice is the Transmission Control Protocol, or TCP. I want you to think of TCP as the meticulous, registered mail courier of the web. This quote really hits the nail on the head. TCP is what we call a connection-oriented protocol. Its entire reason for existing is guaranteed delivery, and it takes its job incredibly seriously. With TCP, both ends of the connection establish a dedicated line, and they keep a really careful inventory. If a packet of data takes a wrong turn at a router in Chicago and gets lost, TCP notices, stops, and resends it before moving on.
Now, what's really interesting here is just how thick and complex the TCP header actually is. Look at all those fields. You can see the sequence number, which meticulously numbers every single byte of data so it can be reassembled in perfect order on the other side. Then you've got the acknowledgement number, which is basically the receiver signing for the package. All of these built-in error checking and sequencing features, that's the secret sauce to TCP's absolute reliability. Because of all those fields we just saw, TCP boasts some seriously powerful core features. Not only does it guarantee in-order delivery and error checking, but it also features flow control and congestion control. What that means is TCP acts kind of like a polite house guest. It constantly monitors the network traffic and dynamically adjusts its transmission rate so it literally never overwhelms the receiver or bottlenecks the network. This is exactly why a file transfer arrives perfectly intact every single time.
Section 3. The TCP three-way handshake.
But how exactly does TCP set up this incredibly reliable connection? Well, it uses a very specific mechanism to establish trust before it ever sends a single byte of actual application data. This is the famous TCP three-way handshake. It's very much like a formal telephone greeting. Step 1. The client sends a SYN, or synchronize packet, essentially saying, "Hello, I'd like to start a conversation, and here is my initial sequence number." Step 2. The server replies with a SYN-ACK, responding, "I acknowledge your request, and I am ready. Here is my sequence number." Step 3. The client sends a final ACK, confirming receipt. Boom! Only now is the connection officially established. Now, while this three-way handshake provides an incredible foundation of trust and perfect order, it definitely has a cost. All of this back-and-forth negotiation, it takes time, it adds overhead and latency. If you're just trying to send a super quick, time-sensitive message, TCP's formal, drawn-out greeting process can feel agonizingly slow. And that perfectly sets us up for our second courier.
Section 4. UDP, the speedy sprinter. Enter the User Datagram Protocol, or UDP. If TCP is the meticulous registered mail courier, UDP is the fire and forget sprinter of the Internet. I absolutely love this analogy of shouting across a room. UDP is connectionless. There's no handshake. There's no polite introduction. It just starts blasting data at the receiver as fast as humanly possible. If a packet gets lost along the way, UDP doesn't care. It's already moved on and is talking about something else. If packets arrive out of order, UDP just shrugs and leaves it entirely to the application to figure it out.
And this brilliantly illustrates the difference. Compare this streamlined UDP header to that massive TCP header we looked at earlier. It is incredibly lightweight. You've just got the source port, destination port, length, and a basic checksum. That is the whole shebang. No sequence numbers, no acknowledgements. By stripping away all of that memory and error correction, UDP achieves blazing fast speeds.
Because it lacks all that heavy overhead, UDP is defined by its sheer speed. It doesn't wait around to see if the network is congested. It just sends. It doesn't bother retransmitting lost data. The result? Incredibly low latency. It's specifically designed for applications where getting the data right now is vastly more important than getting the data perfectly.
To really cement this in our minds, let's look at the contrasting personalities of these two protocols. TCP requires a signature, it meticulously checks every package, and it politely slows down in heavy traffic. UDP? UDP basically tosses the flyer out of a moving car window, completely ignores the traffic conditions, and just keeps its foot pinned to the gas.
Section 5, Real-World Protocol Trade-offs. Let's see how these deep technical differences dictate our invisible, everyday online experiences. Well, you're going to want TCP anytime reliability is absolutely non-negotiable. Think about downloading a massive game patch or executing a financial transaction with your online bank. I mean, there is no way you'd want a dropped packet to corrupt your file or, worse, mess up your bank balance. The same goes for web browsing and sending emails. TCP is really the only logical choice here because absolute accuracy is required.
So the crucial point is, when does speed win? Well, UDP is the undisputed champion of real-time interaction. In an online multiplayer game, you need to know exactly where the enemy player is right this millisecond. If that data packet gets lost, you definitely don't want the game to freeze and wait for it to be resent. By the time it finally arrives, the player's already moved. In video conferencing and live streaming, a dropped frame is vastly preferred over a delayed one. That is exactly why UDP is used.
Here is a quick summary cheat sheet wrapping up our explainer. Basically, TCP gives you a guaranteed, reliable connection at the cost of speed. UDP, on the other hand, gives you blazing fast connectionless transmission at the cost of reliability. They are two entirely different tools designed for two entirely different jobs, working side by side to deliver the modern internet experience we all rely on. But I've got a thought to leave you with today. As our digital world increasingly demands both perfect reliability for data and instant speed for real-time media, the landscape is starting to shift. Emerging technologies are already trying to blur the lines, building reliability straight on top of UDP's speedy framework. So could hybrid protocols eventually make the classic TCP versus UDP debate a thing of the past? It's a truly fascinating question, and one we highly encourage you to explore further. Thank you so much for joining us for this explainer.